whenever we come across alcohols, we need to see chemical reactions in two different types of cleavages. One is between oxygen and hydrogen, the other one is between carbon and oxygen. So first let us see how the OH cleavage bonds, cleavage will lead to certain reactions. First, if any alcohol is treated with a metal, metals which could be sodium, potassium, or aluminum, they will provide electrons to this hydrogen and remove it out as H2 gas, while the rest of the part will be remained as alkoxide, RO minus. Okay, and therefore, next, if you have an alcohol, you react with 2 moles of aluminum here, so that will convert into an alkoxide, and H2 gas is evolved. Got it? So logic
Yes.
is the same. They are metals are providing electrons to them. Next one is alkylation. Alkylation is where you will try to convert an alcohol into an ether. See what you do. First, we react with sodium, so we will get hydrogen gas and RO minus. The RO minus is always called as alk oxide. Okay, this is alkyl group converting into an oxide form, so that's why it is called alkoxide. Sodium alkoxide. Okay, so sodium alkoxide, in case if at all you push some alkyl halide into it, RO minus being a strong nucleophile, so it is a strong nucleophile, will definitely try to attack R and remove this X. And because it is a strong nucleophile, it will favor an SN2 mechanism. Got it? That's how you will get an ether. And this process is called Williamson ether synthesis. This we learned it earlier as a part of alkyl halides also. Okay.
Yeah.
The same type of reaction can be achieved even when you have uh, sulfate esters. So suppose this is a methyl sulfate ester. So instead of these two hydrogens, here we have methyl groups. So again, if at all you use a small amount of OH minus, this OH minus can take this H plus, converts into an alkoxide, and the alkoxide can attack. Or even if OH minus is not there, the reaction will take place, but it will be a slow process. That's all. So alcohol will attack on methyl group and making this as O minus. Why this is easy to break is because this part of sulfate is a very good leaving group. Any sulfate form is a very good leaving group. Okay. So this can leave easily. Oxygen can attack here and you will get this form. And thereafter, if you use a base now, it can take away this H plus, or O minus from this sulfate can take H plus, and the remainder will be ethers. Okay. And 1 mole of this sulfate ester can react with 2 moles of this alcohols. Okay. So you can get 2 moles of this plus SO4 2 minus. Done. Next, I can use diazomethane to make a methyl ether. Methyl ether means I would have diazomethane in this form, CH2 minus and N2 plus. This is the structure of diazomethane. And since you have a CH2 minus, which is a very strong basic nature, we'll extract H plus first. See, as it extract H plus, it will become CH3N2 plus. And now N2 plus is an extremely good leaving group. So O minus can attack on methyl and relieve that N2 gas. That's how you'll get methyl ethers. Okay. Next one is bimolecular dehydration. This we have seen as a preparation reaction also. So in case if you have an alcohol and you're reacting with a concentrated H2SO4, but you are maintaining certain temperature. In this case, the temperature which you are maintaining is 413 kelvins. At this temperature, you will tend to get more ethers than alkenes or any other product. How's the reaction proceeding? Since it is in an acidic medium, the alcohol will take H plus, gets OH2 plus. Then the second mole of alcohol will attack the carbon, okay, and as it attacks, the water will come out of it and you will get a oxygen linked group here. So whenever you have an oxygen plus ion, this is called oxonium ion, okay? Whenever it is a plus charged one. So from the oxonium ion, deprotonation, that means H plus will come out and ends with an ether form. Here, beta. Now these cases are pretty much valid only for a basic or simple alkyl groups like methyl or 1 degree cases. But in case if there are bulkier groups, then elimination is always more favorable even at lower temperature. Okay.
Yes, sir.
Suppose if I take ethanol and react that below or up to sorry less than 140 degrees, then first you will get a salt form, right? Because this oxygen can take H plus and the rest part will be HSO4 minus. So this will exist like a salt form here. And then if you maintain at over 140, it will convert into an ether form. And if you are taking it beyond 140 degrees, then the major product will be more of alkene. So dehydration will take place, which is OH from here and H from other carbon, right? So that way dehydration is more favorable. So you can see if I take 2 moles of this with concentrated H2SO4, first protonation will take place. And since you are using at high temperature, dehydration will happen first, water will be relieved. You get a positive charge. Positive charge can be further migrated, that means it can be rearranged. So from a primary position, it can be rearranged to tertiary position. Then the lone pair of oxygen will attack here, and while it is attacking, it will attacking like a base, and it will extract hydrogen from this end, which makes it into an alkene form. And this part will convert into an OH2, which will relieve again as this will be starting to get into carbocation again with H2O. So that means the next molecule is ready again. Correct? The next molecule is ready again to get into alkene form. Done. This is how bimolecular dehydration is observed. Okay, beta.
Yes, sir.
Next. What is acylation? Acylation means on the alcohol part, you are substituting C double bond O. That is called acylation. Any acyl means C double bond O group. Okay. So you are making an acyl to get substituted. This substitution reaction, if you are doing with acids, this is called esterification. Esterification. Okay. So in esterification, what you will notice is that if you have an alcohol reacting with R-COOH, the H from here and OH from here will be relieved, and that converts into an ester form. Okay. So it is as if the acid is losing OH and the alcohol is losing H. Okay. Right. If you are doing it for simple alcohols and acids, we call it as Fischer esterification. And esterification is only favorable in acidic condition, not in basic medium, neither in neutral medium. Okay.
Okay.
Esterification is a reversible reaction, which means this ester can again uh, react with water and convert or retract back to acids and alcohols. So if you want to increase the quantity or make the reaction to move more in the forward direction, the best thing to do is that you try to siphon this off, which means as it is forming, you start distillating. So as you start distillating, this will keep on coming as vapors. And as the vapors will keep coming, the reaction will keep going in the forward direction. Otherwise, this will have more, if you let it have more interaction with water, again the reaction will go backwards. Okay. Right. Next. You see how the mechanism takes place. Acids, when you react with H plus, the lone pair from oxygen will take H plus and converts into this compound, which is having a resonating structure of a very similar structure, right? You can see this structure and this structure are exactly same. If two resonating structure looks alike, we call them as equivalent resonating structures, correct? And you know that equivalent resonating structures normally dominate over the other form of resonance. And that's one of the reasons why this lone pair is not attacking, but this lone pair is attacking. Okay.
Yeah.
And that's how you will get this, intermediate. Now, once you get this intermediate, now this carbon starts to gain sufficient delta positive because of the adjacent oxygen having positive charge. Okay. Charge will
Yeah.
get induced on the carbon. And that's when the alcohol as a nucleophile will attack. As a nucleophile, it will attack on that carbon. And as it attacks, the sp2 carbon is now converting into an sp3 carbon. Okay. And after attacking, you notice this oxygen has positive now. So the adjacent oxygen. Now adjacent oxygen means this and this are both at the equidistance, isn't it? So you could choose any one of them. Understood? You could choose any this OH group or this OH group. One of them will definitely take H plus from the incoming alcohol and converts into OH2 plus. This internal movement of H plus is called as intramolecular proton transfer. And because of which you will get this as OH2 plus. Okay. And now this lone pair which is present will start to push the electrons towards carbon, noticing that H2 is a good leaving group. So the water molecule will come out and you will get this ester form, protonated ester form. And slowly in the solution, it will shred off this H plus and start giving a fruity smell vapors or fruity vapors. Okay, fruity smelling vapors. And that is a formation of ester. Okay. So very important to understand esterification is a three-step mechanism. First step is protonation. Second step is nucleophilic addition. And nucleophilic addition is always going to be the slow step. And since during the reaction, during this mechanism, an sp2 carbon is converting into an sp3 carbon, thereafter a leaving group is going, which means, have you noticed from sp2 eventually again we got to sp2 only. And this group has left and the other group has substituted, which means there is a substitution reaction overall, but it is going through a intermediate where sp3 carbon is converting into an sp2 carbon is converting into an sp3 carbon. So this type of mechanism is called SNTD. Okay,
Okay.
clear? This is called SNTD. TD means tetrahedral formation. So you can say it will form a tetrahedral form. Clear?
Yes, sir.
Right. So last step is what, beta? Dehydration. See, overall steps I'll tell you. First is protonation because you're adding a proton. Second step is nucleophilic addition. Okay. Next, third step is intramolecular proton transfer. Fourth step is dehydration. Fifth step is deprotonation. Okay. So in short, actually there are five steps, but
Yeah.
major steps are what? Major steps are these three. The one is protonation. Next one is Next one is nucleophilic addition, then dehydration, and lastly deprotonation. In alcohols, this is one of the areas where mechanism becomes important. Okay.
Yeah.
So I hope you understood the mechanism. It's not that difficult to digest as well. Okay. It's easy.
Yeah.
Just you need to understand the steps thoroughly. Okay.
Yes, sir.
One thing is for sure, because this is a rate determining step, you expect that this R as well as R dash should be as small in size as possible. Otherwise, they'll start repelling with each other, isn't it?
Yeah.
So, which means you expect the acids to have a smaller size, which means it could be hydrogen, methyl, ethyl, propyl. If you compare these four, obviously, formic acid will have more reactivity because of less
Right.
crowding group. Same case with methanol, alcohol also. Methanol will have more reactivity than ethanol, then propanol, then tert-butanol. Correct? So steric hindrance is an important factor here. Okay. Just a second. Yeah, let's see. Now, suppose if this is a alcohol part and this is an acid part, you will notice that what is going away from acid and what is going away from alcohol. Alcohol से H जा रहा है, acid से OH, right? So that means this oxygen will be connected to this carbon. So this is a 100% product you will get. Is that clear?
Yes, sir.
Now, in the second case, imagine this OH is going and this H plus is going. So you would get this one, but this is not 100%. Why? Do you remember that after protonation, this group and this group are alike, right? So that means this OH2 can go, this OH2 can go.
Yeah.
So chances are 50% you will get oxygen, which is isotopic, or 50% you can get oxygen, which is non-isotopic. Correct?
Yes, sir.
Same case in the last one also. So you'll get 50-50 percentage. Okay. Now, overall reaction of esterification is a irreversible process. But what if I want to make it more, reversible process. But what if I want to make it more irreversible? To make it irreversible, instead of taking acids, you directly take acid chlorides in pyridine. Okay. So when you take that, what happens? First, you see this H and Cl will come out as acid. But problem is, if esters find that there is an acid, they'll immediately try to go backwards. They will react and again they'll go backwards, correct? So you want acid to get neutralized. So what is the salt?
Yeah.
What is the solvent you take? Pyridine,
Hmm.
correct? So what will pyridine do? Pyridine immediately neutralizes that HCl and convert into pyridinium chloride. Got it?
Yeah.
So that's the importance of pyridine here. Okay. So now the reaction cannot happen backwards. Clear? Why? If Cl wants to go attack and RO minus has to come, Cl is a better leaving group. So this cannot attack. RO minus is a weak leaving group. The reverse is okay. That means if you have an acid chloride, RO minus can attack. But Cl minus attacking and RO minus leaving is not possible. Okay.
Yeah.
So therefore, this is a irreversible reaction. And you could also use, instead of acid chloride, you could also use anhydride. So in the case of anhydride, one will become an ester, the other one will become RCOO minus. Okay. RCO
Hmm.
minus is very self-stabilized because of its resonance. So it will hardly go and attack back. So this will also remain irreversible. Okay. Clear, beta? Right. See, this is a group which is directly going to connect to alcohol. This is the group which is connecting into alcohol. So this is used as a method to determine how many polyhydric groups we have. That means how many OH groups do we have in a compound. For example, if I take this compound, especially in sugars, we will have a lot of OH groups like glucose, sucrose, fructose, starch. We will have a lot of OH groups.
Yeah.
So if I want to know how many OH groups are present in a particular sugar, let's say it has n number of OH groups, then I will react with excess amount of anhydride. So all the hydrogens here will be replaced by AC. AC is CH3 C double bond O.
Hmm.
Got it? Now what is the molar mass of AC? Molar mass of AC is 43. And that is replacing one hydrogen. Remove that. So -1. So how much is the extra mass that it is gaining? 42. So that means that every OH group, you will get extra 42 grams of extra amount of mass gained on the ester. Clear, beta?
Gotcha. Yes, sir.
So now suppose initially if this molar mass of this compound is M1, And after the reaction, molar mass of the new crystal form is M2. Now the difference divided by 42 should give you number of OH groups, right?
Mm.
Because 42 times of N is the difference. So that
Yeah.
N represents the number of OH groups. Clear, beta?
Yes, sir.
No. This was recently asked in JEE that if you have a OH group on one end, NH2 group on the other end, and then you're reacting with acid, chloride, or anhydride, but you are taking only one equivalent in pyridine. So where does the reaction happen? Now remember, here all you need to check out is which is a better nucleophile. See, oxygen's lone pair attacking or nitrogen's lone pair attacking. Which one is a better donor here? Nitrogen, right?
Yeah.
Because electronegativity wise, nitrogen is less electronegative than oxygen. So nitrogen is a better donor. So what is most likely to attack first? Is it oxygen or nitrogen then? So nitrogen. So
Nitrogen.
nitrogen will attack. So amide bond will be more relevant as compared to that of an ester bond. Clear? So keep
Yes,
that
sir.
in mind. First priority is always towards formation of amides. Okay, beta?
Yes, sir.
Right. So this is one example that was given in JE again. This was a JE question that 92 was the molar mass given and 218 was the molar mass given, and you are supposed to find what is N value. So how many hydroxy groups we will have? 3. Okay. Glucose question is also very, very relevant one. So if you have 180 and after acetate formation it is 390, then how many OH groups glucose possess? Glucose will have 5.
Yeah.
Yeah. Now, if you compare the reactivity towards esterification, a group which is donating will decrease the delta positive on carbon. So that will be less reactive. And a group which is even donating by resonance, that will be even more less reactive. Correct? So if you compare acetic acid and benzoic acid, acetic acid will make a better esterification reaction. Okay. Next,
Yes, sir.
if you have one chlorine, if you have 2 chlorines and 3 chlorines, so obviously 3 chlorines will be more strongly withdrawing. That increases
Yeah.
delta positive on carbon. So the reactivity of this acid will be more. Okay.
Yes, sir.
Right. Next, if mineral acid mixed H2SO4 is used, imagine instead of directly using H2SO4, we are using HCl with H2SO4. Then the name of the esterification is Fischer-Spear esterification. Fischer-Spear esterification. Rest all everything is same. Next type of esterification is trans esterification. That is, if you have an ester react with an alcohol. Now what happens? There is already an alkoxy group. Now this alkoxy group can be replaced by this alkoxy groups in the same acidic medium. But this is
Mm.
only possible if the alcohol content is taken in excess. Obviously, otherwise this is also an alcohol and this is also an alcohol. So what is the motivation for this alcohol to leave? The only motivation is if this is coming in excess. Okay. So then the reaction can go in the forward direction. So what is the minimum ratio that we need to maintain? 1:7. So for every 1 mole of this, I should have at least 7 moles of this. Clear,
Okay.
beta?
Yes, sir.
Any doubts so far in esterification?
No, sir.
Can we go ahead?
Yes, sir.
Right. See.
So,
Hmm.
little off topic, but the tests that you had posted.
Notice esterification cannot be carried in basic medium. Okay, because in basic medium directly base will react with acid. So then how does the esterification takes place, right?
Yeah.
Right. Second thing is if you take a triglyceride like this, these are called triglycerides, okay, which we call it as cholesterol in general, right?
Mm.
So that when you add it with excess amount of ROH, right? So in that case, what do we get? All this part will convert into these esters, and this part will convert into an glycerine. Got it?
Yes,
So
sir.
now, once you get this ester form, once you get this ester form, if at all you react with NaOH, that will convert into 3 moles of this acid salt. These are called fatty acids. Correct?
Yeah.
Here, these are the deposits which which will cause blocks in the blood. Here, so that's why we say generally cholesterol should be
Yeah,
maintained
yeah.
at a lower levels. Correct? So,
Yes.
so point is here, one thing you are creating in your bloodstream, you might also be creating a thick solution which is glycerine, right? Which is also not good.
Yeah.
Understood? And in fact, this is very rarely, I mean, the quantity wise, it is very less though. But this is a major reaction that happens in chemical industries where your objective is to prepare glycerine and objective is to prepare soap. This is a composition of soap.
Oh,
This is the soap which we use, correct? This is called sodium stearate. C17 CO minus is sodium stearate. Clear?
okay.
So soaps are made up of this complex triglycerides, okay,
Mm.
which we consider as wax, isn't it? That
Oh,
waxy
okay,
part.
okay.
So from there, as we react with directly, you can directly react with acids also or in base
Mm.
also. So you can directly react in NaOH, and as you react with NaOH, you will directly get this salt form, soap form. Okay,
Okay.
notice. Esterification can be observed internally also. That means internally we have an acid and alcohol. In acidic medium, this alcohol can connect here and convert into this ester form. Okay. Now, when you get this ester form, the naming will always start from the oxygen end. Okay, beta. So
Mm.
like this, we have 1, 2, 3, 4, 5. Correct?
Yeah.
This is the way we have it. So it is with respect to oxygen. The first one is alpha, beta, gamma, delta. Okay, clear.
Okay.
So this is called delta lactone. Lactone is a common name for cyclic esters. Okay,
Yeah.
right. Next, notice what is reactivity involving CO bond cleavage. So far we saw O and H bond cleavage. Now we will see C and O bond cleavage. Okay. For that to happen, first we need to protonate, get H plus on alcohol, and then remove it out. So the removal can be done both via SN2 mechanism or via SN1 mechanism. If this alcohol is of 1 degree, usually SN2 is more preferable. If it is of 2 degree and 3 degree, SN1 is more preferable. Okay.
Okay.
And reactivity wise, if you notice, 3 degree will have more reactivity than 2 degree than 1 degree. Got it? And in case if you compare uh, halides, which includes HCl, HBr, and HI, okay, HI is more reactive than HBr than HCl. Okay,
Yes, sir.
clear, beta? Why is it more reactive? Because HI bond is weaker. Okay, mind you,
Yeah.
this comparison is only in concentrated acids. Okay, if you take aqueous solution, the reaction will again go backwards and you will get alcohols only. Hmm?
Mm.
So it should not be taken in aqueous solution. Here. Now,
Yes, sir.
so much so that if you take a HCl and try to react, you will not see SN1 reactions at all like this. Suppose if you have OH and then you are trying to react with HCl, correct? And you are expecting this to become OH2 plus plus Cl minus. But this reaction won't take place because without water, HCl will have a very strong bond to break. When you add
Mm.
it to water, water is helping to break H plus and Cl minus. Okay. But this reaction is not going to happen that easily. That's why you need to use some Lewis acid. Okay. On using the
Okay.
Lewis acid, like ZnCl2, will take these chlorides, convert into a complex, and relieve the hydrogens as H2 H plus ions. Okay. Clear, beta?
Yes, sir.
That's how your protons will be available here. So I need to have an anhydrous zinc chloride, and this composition, that is concentrated HCl with anhydrous ZnCl2, is called Lucas reagent. This is called Lucas reagent. Okay. And this could
Okay.
be best used for identification of the position of alcohol, whether it is at 1 degree, 2 degree, or whether it is at 3 degree. Okay.
Okay.
If it was at 1 degree, the reaction where protonation will happen and then removal of this water and then attack of chlorine is a very slow process. Either the reaction will not happen only, or
Hmm.
it will take a lot of time even on heating.
Right.
Okay. And since there is no water, this alkyl halide which is forming slowly in this alcohol solution will be a white color precipitator. Okay,
Hmm.
white color, what do you say, buttermilk type of solution starts forming. That is called turbid. Okay, so it will
Okay.
start making a turbid form. Now, if it was a 2 degree, the turbid formation happens relatively at a much faster, but it is still taking 2 to 5 minutes. Okay,
Okay.
but imagine if it is tertiary, instant carbocation will form, instant chlorine will attack, and you will get the turbid immediately. Hmm?
Hmm.
A cloudy, white cloudy form is
Yeah.
observed, right? So this
Yeah.
turbid formation is immediate if it is tertiary, which means it's basically not
Mhm.
tertiary, it is about stable carbocation, isn't it?
Yeah.
Because tertiary is at a very stable carbocation position, that's why it is happening faster. What
Hmm.
are the other cases which will be very stable in carbocation positions? That includes allyl, benzyl, CPM form, correct? Cyclopropyl methyl. These are all stable carbocations, right? That's why these, including 3 degree, they will give you turbid way much immediately. Okay.
Hmm.
While the other cases you will see it will take long time. Correct. So
Okay.
you can see alkyl halides having more than 6 carbons are insoluble and cannot be distinguished easily. Okay. So if you
Okay.
have an alkyl halide more than 6 carbons, so it becomes very difficult to analyze only. Yeah, okay, because the reactions will take a longer time in all the cases. Okay.
Okay.
Right. Next. The next tip is about dehydration. Okay. Dehydration is removal of water. So
Yeah.
I take OH and H plus from the adjacent positions, remove that out and get a double bond.
Yeah.
Now you just need to remember the uh, uh, reagents. See, if at all I take a concentrated H2SO4 or a concentrated H3PO4 or only Al2O3, okay, these three specifically are for SN1 type of reaction. Sorry, E1 type of reactions.
Hmm.
E1 means you expect them to form carbocations
Yeah.
and then carbocations will undergo rearrangement. After that, you'll get a double bond form. Okay.
Okay.
But in case if you take Al2O3 with pyridine, hmm, it will make an E2 mechanism with Shezef as the major product. Hmm. And if you take thorium dioxide, it will become E2 mechanism with Hoffman as major product. See, more than trying to figure out how the reaction happens, best thing is to remember the reagent and what is the work it will do. Okay.
Hmm.
So you can notice 1, 2, 3. What are they doing, beta? E1. Hmm?
Even.
Thorium dioxide E2, Al2O3 in pyridine is E2, SOCl2, PCl5, these are all E2. Hmm?
Right.
Clear, beta? So anything
Yes.
of this is asked. Out of all these E2, again, there is only one exception. The thorium dioxide gives major product as Hoffman, rest all will give Shezem.
Hmm.
For instance, if you take this alcohol and you are you are going just beyond 413 kelvins, yeah. So instead of forming ethers, now it starts forming alkenes. So you'll see
Hmm.
alkene is a major product. But if you're taking it 430, ether is a major product. Hmm. Clear now?
Yes. Sir.
Right. Okay. Now, given any particular question, you should be able to answer what is the product that happens to, what is the product you will get. Okay. For example, if at all I have a compound like this here. I have a secondary alcohol here, okay? And then I treat this with Al2O3 and heat. The heat is typically 300 degrees centigrade. Sorry, 350 degrees centigrade. Clear? And then
Yes, sir.
if at all I treat Al2O3 heat in pyridine, if at all I take thorium dioxide and heat, okay?
Yes, sir.
So these three will represent three different types of mechanism. The first one is E1,
Okay.
second one is E2 with Shezev, third one is E2 with Hoffman as a major
Okay.
product. So if it was supposed to be E1, that means you are expecting this to first form carbocation. Yes, correct, beta.
Yes, sir.
If there is a carbocation formation, there is a definite chance of rearrangement. In this case, the rearrangement is basically ring expansion. So you will get positive charge here. Okay. Sorry, on the left hand side. It is the same, but let me write it on the left hand side. Then it will rearrange again. You will get positive charge here. And after this, the elimination will happen. So on heating, you will get double bond here, which is major. Correct.
Yes, sir.
Now, second case, we will have elimination directly because it is E2. E2 will not have any carbocation, but double bond will form here. This is major. What is this one? Shezev.
Yeah.
Third case, double bond
It.
will form, but outward. So this is
Oh,
major. So this is Hoffman.
yes, sir.
So I hope you understood what is to be learned. Okay. So this is
Yes,
a
sir.
type of question that is usually going to be asked. Okay. This is more exam oriented area. Okay. So
Okay.
that means most of the time in JEE exams, mains or advanced, they expect you to understand the hydration way better, which case to be used, what is the product you will get. Okay.
Okay.
Now, next coming to the substitution reactions. Well, I am not using a strong heating here, and I'm just using ether as the solvent in all of them. Hmm? Okay. Except in the last case where I'm using pyridine as the solvent.
Hmm.
Okay. So in that case, when you are using PCl5 alcohol, you will get alkyl chloride, then POCl3 and HCl favored via SN2 mechanism. This is what we learned in mechanism already. I mean, in
Yeah.
alkyl halides already. Okay. For the preparation part, alcohols, when you react with PCl3, will give you this. But here it will take 3 moles of alcohol to get 3 moles of acid chloride. Understood?
Yes, sir.
Next, if you take SOCl2, you will get RCl, SO2 and HCl. This type of mechanism is called SNI. Okay. Let me remind you, we discussed this in alkyl halide though. I'll just quickly remind you what would happen here. Okay. So when let's say I have CH3, CH, here I have, sorry, I'll take with a configuration. I have a CH3 here, H here, deuterium here, and OH here, correct? What will this OH do is that with SOCl2, it will remove out H and Cl, okay? This is what you will
Hmm.
get, okay? Now, this oxygen is trying to push electrons towards sulfur because S double bond O is a stronger bond than carbon single bond O.
Hmm.
That's a motivation for it to start moving towards sulfur. Simultaneously, as it starts moving, this bond will start becoming weaker. And that's when internally, because they are on the same plane, you see this carbon, oxygen, sulfur, and chlorine, they are all on the same plane. So this chlorine can attack from the same direction from where the oxygen is relieving. Hmm, correct? So what would
Yeah.
happen now? You'll have CH3, okay? From the same direction the OH is going. So this will be deuterium. Here it is deuterium. And this will become SO2. Understood now? Hmm? So
Yes, sir.
suppose if this was, plus, that means it is dextro rotation. this will remain dextrorotatory. That means if this is R, it will remain R, or if it is S, it will remain S, correct? So a substitution reaction where a retention is happening, the configuration is getting retention, that is called as SNI mechanism. Okay, do you recall
Yeah.
that? Yeah.
Yes, sir.
If the inversion happens, you call it as SN2.
Yeah.
Okay, and that's what you will typically notice if you are using pyridine. Okay,
Mm.
in the case of pyridine, now what would happen? This HCl which was removed earlier, I told you, right? यहाँ पर एक hydrogen था and यहाँ पर एक chlorine था. Those two has
Yeah.
left. That HCl will react with pyridine and increase the Cl minus concentration. So Cl minus will attack from the back side, removing this SO2. Okay. So
Okay.
that's how you will get this SO2. I mean, that's how you will see this SO2 out and alkyl halide forming. So
Mm.
this goes via SN2 mechanism. Clear, beta? Right? Any doubt with this substitution case?
No, sir.
Right.
Sir,
How beta?
can I please go get something to eat?
Yeah, sure. Please go ahead.
2 minutes, 2 minutes, I'll come back.
Sure. See it, beta. The next set of reaction where carbon-oxygen bond is involved is oxidation. But here it's not breaking. It's not about breaking, it is about oxidizing. Now, whenever I say oxidizing, please notice this case. Suppose if you have a carbon connected to oxygen and hydrogen, right? Let's say these are hydrogens, correct?
Mm.
Now, how do we find the oxidation state of carbon here? If you may have learned from redox, you know that carbon is slightly more electronegative than hydrogen, correct? And we always assign the oxidation state based on electronegativity differences. So I can say carbon in a way is gaining 3 electrons from 3 hydrogens and it is losing 1 electron from oxygen. That makes it -2 oxidation state, correct?
Yeah.
Sorry. Now, if it get oxidized, so it might get H double bond O. This is one part of oxidation. The other part is H uh, H double bond O and OH. So this is like a partial oxidation. This is like complete oxidation. Correct. So if it is a partial oxidation, now what is the oxidation state here? On this carbon, it is like gaining 2 electrons and losing 2 electrons, isn't it? Because
Yeah.
double bond is there with oxygen means 2 electrons are lost to oxygen and 2 electrons are gained from hydrogen.
Mm.
Make sense? Yeah.
Yeah.
Right. On the other hand, if you notice here on this position, it is like gaining 1 electron and losing 3 electrons. Correct. So how much is the oxidation state now? +2. Okay.
Mm.
So this is what I want you to notice carefully, that there is always a 2 electrons which is being squeezed out of this. So for every 1 mole of alcohol, when it is getting oxidized to aldehyde or a ketone, so how many electrons it is giving, beta? 2 electrons it is giving in this redox
Mm.
reaction. Okay,
Yeah.
right? So one molecule always to aldehyde it is 2 electrons. If it is going up to acid, it is 4 electrons. Okay, so you
Mm.
can see 2 + 2, total 4 electrons from alcohol to acid, alcohol to aldehyde 2 electrons. Okay. Or going ahead, when we learn about aldehydes also, we learn aldehydes to acid oxidation is 2 electrons. Got it?
Yeah.
See. Now notice, if you have a 1 degree alcohol and I make an oxidation, what exactly is happening between these two? ध्यान से notice करना. Imagine like this hydrogen is removed and this hydrogen is removed. So what are we getting? Double bond, right? So
Yeah.
it's like removing 2 nascent hydrogens out of it. Every nascent hydrogen is equivalent to saying 1 electron. So 2 nascent hydrogens means 2 electrons. Okay? So you can see 2 nascent hydrogens are going out, converting into an aldehyde. And then if it wants to be, sorry, if it wants to get further oxidized, you will notice that this will convert into an acid form. Okay.
Mm.
So you notice this here, same logic here. two hydrogens, you will get aldehyde, then you will get acid. If you get this alcohol, remove out these two hydrogens, you will get ketone. Now the problem with the ketone is this is a carbon-carbon bond, right? So usually it becomes very difficult to oxidize it to acids. So more or less, when ketones are there, right, you will not do further oxidation, or you can't do further oxidation unless it's a very rigorous condition, which is the
Mm.
last case. See, if you have a ketone and you want to make an oxidation in this case, then there is no other alternative but to break the carbon-carbon bond. Okay. Now, what happens is when you take a rigorous condition like a very hot solution of KMNO4 or K2Cr2O7, then this ketone can be converted into an enol form. Okay, this can be converted into an enol form. This phenomena is called tautomerism. Okay, so if you recall it, that's good. Otherwise, just remember the phenomena for now. It is called
Yeah.
tautomerism. So a tautomerized, and wherever there is a double bond carbon, we learned this in alkenes that they will break out easily with
Yeah.
KMNO4 or K2Cr2O7. So that's why this bond will break. This part will become acid and this part will become acid. Clear? And if it is a single carbon, that acid will keep on oxidizing up to the point where it becomes carbon dioxide.
Mm.
Okay? So this is called rigorous oxidation using KMNO4. Okay. Now in this oxidation, suppose if at all I had an little unsymmetrical ketone this way, yeah, then I'm using alkaline or acidic KMNO4 and strong heating. Strong heating, what I said, you first imagine it in terms of alcohol. So you can put this as OH, correct? But enol form. Enol means double bond can come here or double bond can come here, right? Now, getting a double bond here is more stable, isn't it? Because यहाँ पर तो hyper conjugation नहीं है. But if you put
Yeah.
double bond here, you'll have a hyper conjugated support. So you need to make a more stable alkene, right? And this is that more stable enol form. And then you start breaking the bond. As you start breaking the bond, this part will become acid, this part will become acid. So basically, you will get 2 moles of CH3COOH. This is the product. Okay. And this is major product here. Now, what is a minor product? That means getting an enol form on this side and then breaking. So what is that we will get? We will get propanoic acid and CO2, correct? Single carbon will convert into CO2. Now,
Mm.
this is something called Popov's rule. What is Popov's rule? Popov's rule suggests that whenever you make an oxidation of an unsymmetrical ketones, it will tend to go in the direction where you will have a smaller carboxylic acid. Can you see this is smaller carboxylic acid than propanoic acid?
Yeah.
So acetic acid is smaller, propanoic acid is larger. So therefore, size wise. So this is following Popov's rule. So this one is following Popov's rule. This one is not following Popov's rule. Okay.
Okay. Yeah.
So follows Popov's rule. Correct. Although in JEE mains directly the wording is not asked, but unfortunately the reaction is asked. So you can understand what is a product there. Okay. So you need to figure out a major product. Next, if you have a tertiary alcohol, if you have this tertiary alcohol, then you will not see any oxidation happening because there is no hydrogen only to remove out. Okay. But again, if you make an extremely rigorous condition, then the entire carbon-carbon bond could break, convert into an alkene, and thereafter it will convert into acids. Okay. But this is very rarely observed, so don't worry about it. Okay.
Okay.
Now, these are the typical reagents that you need to remember, which will give different products. So, how do you remember this? First set, this is the set of first three reagents, which is alkaline or acidic KMnO4, right? Then simply writing it as KMnO4, sorry, K2Cr2O7 in acidic medium. That I have not written, but it is one and the same. Like here, this one is same as, or I'll write it as or. Okay, or we can simply write this as K2Cr2O7 in acidic medium. So because the logic of this acidic medium or this acidic medium is same, they both will get oxidized similarly. So if I take these reagents, or if I take CrO3 in acetone, adding small amount of dilute H2SO4, then this particular reagent is called Jones reagent. This is called Jones reagent. This has some advantage over this one. Okay, what is that? We will see. Okay, so you will notice these three are reagents which will oxidize almost everything up to acids. Then we have these reagents PCC, PDC, copper, and heat. They will only oxidize up to aldehydes. They cannot take it further to acids.
Okay.
Okay. So in case if you have a 1-degree alcohol, you will get aldehydes. 2-degree alcohols, ketones. 3-degree alcohols, no reaction except for copper and heat. Copper and heat will give you dehydration. Okay, OH and H from the from the beta position, he will remove that H and convert that into an alkene. Okay.
Okay.
Right. And lastly, now this is important to note. If you have a double bonded carbon, see, the mild reducing agents, mild oxidizing agents will not have any role. But you know that KMnO4, K2Cr2O7 will break it, correct? That's why
Yeah.
these two are breaking. But if you take Jones reagent, hmm, Jones reagent will not make any disturbance on the double bond. That's why it is slightly different than this one. Clear with that point? Rest all of the reactions are same. The change come in these two positions. Okay,
Okay.
clear?
Yes, sir.
Right. Okay. Now I'm skipping out mechanism because it is not essential right now. Got it? So you just need to
Okay.
know the reagents as well. That's it. Okay. You need to know what is the reagents like. Okay. The alternative reagents. PCC means pyridinium chlorochromate, hmm, which is CrO3 with HCl with pyridine, but no water. Remember, there should not be any water. If you are a mild oxidizing agent, that means there should not be any water content in it. So this is what happens. This is pyridinium chlorochromate. Then this is usually yellow color solution. This is directly the structure has been asked in mains multiple times in the recent JEE only. So remember that they might
Okay.
ask you the structure directly. What is PCC? PDC. What is PDC? PDC is pyridinium dichromate. This one is chlorochromate. This one is dichromate. Clear? That's why it is PDC. That is PCC. Okay. So in case of PDC here, you will see pyridinium dichromate. Clear? There is other reagents like Sarrett's reagent, Collins reagents. Okay. Sarrett's reagent is taking that CrO3 with pyridine, correct? But without any HCl or without any solvent. That is called Sarrett's reagent. If you add the solvent as CH2Cl2, that will become Collins reagent. But don't worry about it. These have been deleted from your syllabus. They will not be asking it. But just
Okay.
for advance, when we revise it, we will just recall these words again. Okay.
Okay.
Okay. Mainly what you need to remember is PCC and PDC. Okay, beta. Okay.
Yes, sir.
Last one is Jones reagent. Like I discussed, Jones reagent that it is a strong oxidizing agent. It will convert 1 degree to acid, 2 degree to ketones. And important part is when you have a double bond, it will not disturb that double bond. The rest of the alcohols part that will get oxidized. Another
Okay.
important part of Jones reagent is if the alcohol is at a benzylic position or at allylic position, then it will not go up to acids, it will remain only up to aldehydes. Okay, it will only
Okay.
remain up to aldehydes. So this is the part. Next, check out catalytic oxidation. And this is what we notice with copper and heat. Alcohols, when you react with copper and heat, you'll convert into aldehydes, giving away H2 gas. And if at all we take secondary alcohol also, it will give H2 gas and converts into ketone. But if you take tertiary, it will, instead of giving H2, it will become H2O, and this will give you ketone. Okay. I know for some reason in recent JEE, these reactions are asked most. Okay. So
Okay.
remember, copper and heat for 3 degree, it is ketone form. Okay. Right. Oxidation with KMnO4, I discussed it already. Mechanism
Yeah.
is not required. Now, this is again an important area where we are using MnO2 and heat. See, MnO2 and heat will only oxidize the allylic position or a benzylic position. That's it. If alcohol is allylic, then only it will oxidize. Otherwise, no oxidation. So again, see, there is an allylic alcohol that will convert into an aldehyde. So this is an allyl alcohol that will become acrolein. Acrolein is that aldehyde form. Here also this is an allylic second degree, so that will become ketone. Okay. If it is
Okay.
allylic tertiary, nothing will happen because there is no hydrogen to oxidize only. Tertiaries
Mm.
will not go anything. Benzylic, that will also get oxidized to aldehydes. Okay.
Okay.
Right. Now, this set of the reactions, just go through it once quickly. You will get a better idea what is the product in all the cases. Right. So these are all few more examples. You can go through it once. Okay. Next. Swan's oxidation is the similar logic as that of PCC and PDC. If you have 1 degree alcohol using DMSO in the presence of this solvent, okay, COCl twice, that is called oxalyl chloride. That means oxalic acid with a chloride group. Okay. And
Mm.
then trimethyl, triethyl amine. So that is a solvent used. So that will make 1 degree to convert into an aldehyde, 2 degree to convert into a ketone, 3 degree no reaction. Opennier's oxidation, I told you already earlier. So MPV reductions, exactly opposite reaction is Opennier's oxidation. So if you take a, a reference alcohol and you're trying to convert that into ketone, then it is an oxidation reaction,
Mm.
right? So in that case, you need to take this acetone in excess so that the reaction can go more in the forward direction, and
Mm.
hence this is called Opennier's oxidation. This is very important reaction now. This is a lab reaction as well. Okay. Ceric ammonium nitrate reaction. Okay. First, check out what is the molecular formula. Ammonium, selenium, and nitrate. 6 moles of nitrate. This is coordinate bond. Okay.
Mm.
Now, when you react this, what would happen is 1 degree alcohol will convert into an aldehyde. 2 degree alcohol will convert into a ketone. And the 3 degree alcohol will make the reaction, right? But does not decolorize. What do you mean by decolorize? See, first ceric ammonium is a yellow color solution beta. You add it into the test tube where alcohol is present. Okay? Then the solution in the test tube will convert into red. Okay? And you leave it for some time or shake it for some time, it will become colorless. Got it? So the red color will start becoming colorless again, wherein this part of the alkoxy group will come out as a radical and then convert into an aldehyde form like this. This will go in the aqueous solution. It will take away hydrogen and convert into aldehyde. Okay.
Mm.
And the oxidation state of cerium, which was at +4 originally, will convert into +3. So it is getting reduced. Alcohol is getting oxidized. Done. When it comes to 2 degree alcohol, again using can test, I will get red color and that also become colorless, but it takes some time. For 2 degree, it will take some time. In
Okay.
case of 3 degree, once this complex is formed, there is no there is no decolorization. So if decolorization is not happening, okay, that means we say it is a 3 degree alcohol. It is difficult to differentiate 1 and 2 degree because it's just a difference in the time. It's very difficult to assess. Okay. But
Yeah.
we can definitely say if the color is not going away, which means it is 3 degree alcohol. Okay.
Okay.
Right. Next, check out bromine water. If you take an alcohol, react with bromine water, which is a mild oxidizing agent, which will convert a 1 degree alcohol to aldehyde, 2 degree alcohol to ketone. Okay. But this
Mm.
is very slow reaction. Very slow reaction. Sorry, not this one. I meant aldehyde. Okay. Right. Clear? So if we take this uh, aldehyde with bromine water, again, this is a slow reaction, but this will convert that into an acid form. Okay.
Okay.
So this is about 1 degree and 2 degree, 3 degree, no reaction as usual. So these are total reactions that will happen as an oxidation. Now, these can be used as a test for various alcohols as well. Check out. First one is a sodium metal test. Sodium metal test is positive because sodium requires a hydrogen which is sufficiently charged and alcohol has it. So it will give you H2 efflorescence. And you know that H2 gas as it comes out of the test tube, if you put a flame towards it will give a pop sound, right? So that's
Yeah.
how you determine H2. So that's the detection. Litmus test, it is neutral, no color change of litmus. Lucas test is to figure out 1 to 3 degree alcohols, correct? So these will give you immediate turbid, 2 degree will give you 5 to 10, 1 degree will give you very long time. Can test, yellow color, solution is converting into red color. That's a detection for 1 degree, 2 degree, 3 degree, important. 3 degree also, अभी तक हमारे पास 3 degree वाला कोई आया नहीं था. Now this has come. Yeah. It is giving that color change. Yeah. Now here 1 degree and 2 degree, K2Cr2O7 is orange color. That will convert into a green color form. Next, bromine in water. Here, bromine water, that will convert into colorless solution from brown. Because bromine water is a brown color, it will become colorless solution if you take 1 degree and 2 degree. Done? These are common tests. But the official test for detection of 1 degree, 2 degree, and 3 degree alcohol is called Victor Mayer test. It's called Victor Mayer test. Okay.
Mm.
So it is if you have 1 degree, 2 degree, and 3 degree. 1 degree will give you red color, 2 degree alcohols will give you blue color, 3 degree will give you colorless. Okay. Right. See, if it is 1 degree, there is a procedure that you need to do in lab. First procedure is you react that with iodine, red phosphorus. Okay. So if you notice, take it. Iodine red phosphorus will convert this alcohol part into iodide.
Mm.
And then on treating with AgNO2, silver Ag plus and I minus can form a precipitate. Okay. So it forms a precipitate and takes this NO2 here. So you'll get a nitro substituted alkane, nitroalkane. And that when you treat with HNO2, nitrous acid, with nitrous acid, this hydrogen and this oxygen will be removed out. This H2O will be removed out and you'll get a C double bond N and OH. And this particular compound is called nitrolic acid, which is blue color. But when you add lastly, when you add NaOH, it will convert into a red color, salt.
Mm.
So ये याद रखना आपको लास्ट में रेड कलर आएगा बस. If it is 1 degree, it will give you red color. Now you do the
Okay.
same procedure once again. With red phosphorus, you will get iodide. With AgNO3, you will get nitro. But thereafter, this time, the OH of nitrous acid and H of this hydrogen will go away. And you'll get NO, N double bond O, which is also again a blue color. But it is not acidic though. So which means if you add with NaOH, nothing will happen. No reaction will take place. Hence, This is remaining at a blue color form only. And lastly,
Mm.
if it is 3 degree first iodide, then nitro will form, thereafter no reaction. So it will remain colorless. So you remember red blood cells, you remember it that way. Okay. Red,
Okay.
blue, colorless. So which
Mm.
is 1 degree, 2 degree, and 3 degree. Clear? So
Okay.
go through it for a minute, then we can go ahead. Check these lab terms. Rectified spirit is 95% alcohol, 5% water. Absolute spirit means 100% alcohol. Wood spirit is methanol. And next, this was the statement given in JE once that CaCl2 should not be used to dry ethanol because it can form complex with ethanol. Hmm? You can use it for drying water. That means you can remove moisture, but you cannot remove alcohol. Next, denaturation of spirit, which means if you want to spoil the spirit, that is alcoholic part, usually that is being done in a unwanted high content of alcohol compounds, because that will be dangerous to consume. So there you can add pyridine with copper sulfate, it will start giving a very foul smell, so it's very difficult to consume. Next, power alcohol. Power alcohol is that E20, which you will find it on the petrol pumps nowadays, or bikes and cars, you'll always get that E20 sticker, which is you will have 80% alcohol, 80% petrol, and 20% ethanol. Correct?
Okay.
Yeah. So now you know that government has made it mandatory to use 80/20.
Mm.
Done, beta.
Yes, sir.
Right. Notice here. The next part of alcohols is about polyhydric alcohols, which means if you have more than two OH groups, two or more than two OH groups. If you have two OH groups, we call that group as glycols. Hmm? You
Mm.
can see if you have an alkene, you react in cold dilute alkaline KMnO4. This is Bayer's reagent. Remember Bayer's reagent? It
Yeah.
will give OH and OH here. So that's how you can get glycolic form.
Mm.
Osmium tetroxide will give you the same. MCPBA will also give you the same, OH and OH. Silver and O2, in the presence of this silver and O2, you will get OH and OH here. These two are same reactions, they will give you anti-addition. Okay. Next we have HOX followed by NaOH. See how it is. I'll show the mechanism. First, when you take HOX, we will have X plus as the electrophile. So pi bond will go attack on X plus. So you will get a 3-membered ring here. Okay. Then
Mm.
OH minus will go attack on carbon, remove out this bond. So you'll get X on this carbon, OH on this carbon. Okay.
Mm.
Then after adding again NaOH will attack here, remove out this X. That's how again you'll get a glycolic form. Okay. So these are all the preparation part. Now see the reaction part. Acha, one more type of preparation is you can take any aldehyde, react with magnesium, mercury amalgam, then hydrolyze it. This we discussed it earlier in the preparation
Yeah.
of regular alcohols only. That two electrons will attack on two different modes and both will get terminated. Thereafter, on hydrolysis, you will get alcohols. And this substituted dialcohols are called as pinocols. Next, if you have diketones also, you use lithium aluminum hydride, this will become alcohol and alcohol. If I use RMGX also, you'll get a tertiary alcohol in this case. Yeah.
Yeah.
If you have C double bond O, I told you this is acyl group. Okay.
Mm.
So it is acyl group, and then you have an alcohol adjacent to it. It is called acyloins. This is called acyloins. So acyloins also on reaction with lithium aluminum hydride or NaBH4, this double bond O will convert into an alcohol form. Next is alpha keto ester. So this is keto and ester form. Lithium aluminum hydride will reduce ester also and ketone also. Again, you'll get alcohol. If I take CH3MgBr, you can convert into pinacols. And next, notice this one, ethylene glycol. Ethylene glycol is having two OH groups on it, correct? This is ethylene glycol. Now, if you do recall from conformations, are you comfortable with this terminology? Conformations? Yeah. There are many types of conformations which you will notice in glycol. If there is an 60 degrees angle which is made between OH and OH groups here in 3 dimension, that particular form of conformation is called gauche form. If the angle is 180 degrees between OH and OH, it is called anti-form, correct? If
Yeah.
the angle is at 0 degrees, it is called fully eclipsed. Okay. If the angle is at 60 here, if the angle where you have H here, because any part of angle, dihedral angle is 0 degrees, then it is called fully eclipsed, but OH should be not on the same direction. Okay. So that is called partially eclipsed. Okay, let me show you one of the partially eclipsed form. So like this, if you have this way, and here only you have other three groups like this. Okay. So
Yeah.
let's say here we have OH. Maybe here we have OH, correct? This is H, H, H and H. Then this is partially eclipsed. Clear, beta? So when you have partially eclipsed, fully eclipsed, gauche form and anti-form, without adding it to water, if you take a pure form of ethylene glycol, then gauche is more stable because in gauche hydrogen bonding is observed. Then anti, then partially eclipsed, then fully eclipsed. But if you take this glycol in water the water itself will help in hydrogen bonding. So it does not depend upon gauche form. The anti will show much more hydrogen bonding with the solvent itself. Therefore, in that case, anti will be more stable than gauche, then partially eclipsed, then fully eclipsed. Okay.
Okay.
Right. So these are the forms you will notice from glycol. It's physically isomerism based things which you need to know from glycol is this one about conformations. Now quickly notice the reactions. All these are alcohol reactions only. If you take SOCl2, you'll get two OH groups replaced by two chlorines with SNI mechanism. Red phosphorus and I2, I and I will come. Now here is important part. If you get two iodines here, right? Two iodines on an adjacent carbon are highly unstable. So you remember vicinal diiodides are unstable form. They will immediately dehydrate. This I2 will come out and convert into an alkene. Always do this. Okay. Wherever there is a iodide adjacent to each other, you can immediately remove them out and convert into a double bond.
Okay.
Now suppose if I add Hi, if at all I'm adding Hi, first you will add H plus here, converts into OH2 and OH2. Both are good leaving groups, remove, and two iodines will come first. So how many moles I consume? 2 moles. Then remove this iodine because it is unstable. Again get an alkene. Now alkenes when easily add on to Hi. So pi bond will attack on H plus, then I minus will attack. So you will get iodide. So how many moles totally consumed this time? 3 moles. This question will be asked that how many moles can be consumed by diols. Okay. Okay, beta.
Yes, sir.
If we use concentrated H2SO4, concentrated H2SO4 is best used for dehydration. So you can notice that one OH here, one OH here, other part of OH and OH here. You can remove water from here, water from here. That's it. So what do I get? I will get this ether form, cyclic ether form. This cyclic ether form is called as 1,4-dioxane. 1,4-dioxane. If I use concentrated H3PO4, see usually concentrated H3PO4 is a polymeric form. It is like a polymeric form. So if it is a polymeric form, then here the dehydration will also happen in a polymeric form like this. If you have an OH here and OH here, the next molecules OH here and OH here. So then the dehydration will happen here, 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 and so on. Correct? So what happens? A chain will form. So you will notice this type of chain is forming with concentrated H3PO4. Okay.
Mm.
Next, with oxalic acid. If you notice with oxalic acid, the OH from here, H from here will make an esterification. So first an ester will form. Cyclic ester will form. Correct. Then if you heat it, remember ester pyrolysis. Correct.
Yeah.
Esters on heating will undergo decarboxylation. So remove this carbon dioxide from here, carbon dioxide from here, and push
Mm.
this here to get a double bond. So that's how you'll get alkenes.
Okay.
Yeah. So this is with oxalic acid. Yeah. Next is with anhydrous ZnCl2. So anhydrous ZnCl2 is best used as a dehydrating agent. So we can take OH and H from here. You'll get an alkene. So alkene with an OH group is an enol. Enol is unstable form. It will tautomerize into convert into keto form. Clear, beta? So
Yes, sir.
these are the reactions for glycol. One important reaction out of it is pinacol-pinacolone reaction. It was honestly it should be restricted to advance only, but they would say this is just a dehydration reaction, so that's how they'll put it in the mains form also, mains reaction also. Okay,
Okay.
check. You know that if you have OH and OH adjacent OH, which we call it as vicinal diols, with some alkyl groups on it, then we call it as pinacols.
Yeah.
Okay, pinacols when you treat with concentrated H2SO4, okay, you will see H plus will get added, water will be dehydrated. Okay, see the mechanism now. First protonation happened, water is been removed, carbocation has been formed, right? So far clear, beta, how the steps are going?
Yeah.
Yeah.
Yes, sir.
Next. Now, if the positive charge comes at this position, yeah,
Mm.
and then oxygen's lone pair makes a double bond with that carbon, वो ज़्यादा stable हो जाएगा because that is an octet completion. Yeah. Okay. So to do that, this methyl will start shifting here. Okay. So
Yeah.
due to this methyl migration, the oxygen's lone pair will push here and convert into a keto form. Got it?
Yes, sir.
And that's how we get a keto form. Then deprotonation will take place, and finally you'll get this keto form. And this keto form is called pinacolone. So it is like pinacol converting into a pinacolone. Okay,
Mm.
pinacol converting into pinacolone. Okay, yeah. Done. So check out these reaction steps once. Okay, so there are
Yes, sir.
basically you know four steps happening. Step one, step two. Sorry, step one, step two, step three, and step four. Okay.
Okay.
So check out that steps quickly once, beta. Then we'll go ahead. First one. Suppose if at all I have mixture of these two different pinnacles. Okay. If you have mixture of two different pinnacles, that does not mean you'll get a pinnacle forming with one group from this first molecule is going to transfer onto the second molecule. That's not going to happen. The transfer is intramolecular within the molecule
Mm.
only. Okay. So therefore, you cannot expect a product like this forming, neither like this forming. Okay.
Okay.
So within the molecule, you should have all three methyls or all three ethyls like this. Okay. That is the first thing. Second thing, if while migration, let's say this is R configured, this is R configured, and while migrating to the adjacent position, the R, this group's R will remain R only. Okay. That
Mm.
does not change. Clear, beta? So the configuration will always be retained. Okay. And lastly, if you have an unsymmetrical form, now notice this is an unsymmetrical form. Now this is an unsymmetrical pinacoles. Here, you first check out which position is the carbocation being stable initially when you remove water out of it. So if I take OH2 plus and remove H2O and you get a positive charge here, you get a positive charge here,
Hmm.
then at this position some methyl has to migrate, correct? But if at all I take positive charge on methyl side here, like this, and this side I have phenyl, phenyl, and OH, then this kind of formation is not observed because on the phenyl side the carbocation is much more stable.
Hmm.
So that's why you should always go with the more stable side, more carbocation which is more stable side. Okay, and from there you decide what is a major product. Now migrating aptitude, which one should be migrated, depends upon this order. Remember this order. Hydrogen is the first one to migrate, then
Hmm.
phenyl, then 3 degree, 2 degree, 1 degree. If you have only phenyl groups, anything which is withdrawing will be less, more withdrawing will be less. Anything which will be donating, like this, methyl is donating, that will be more. P means para, okay? Para methoxybenzene, para methyl benzene, only benzene, okay?
Hmm.
Para chlorobenzene form. This is orthomethoxybenzene. Orthomethoxy is an exception, it will have less migrating nature. But one thing I have noticed in the last 5 years, whenever they have asked, they have actually given this order. So it's not like you have to mug up. But hydrogen, phenyl, and 3 degree. These three things you should know. Hmm? Rest all the time they have given the order, like which one to migrate. Okay.
Hmm.
Now, if you take concentrated H2SO4, both sides are these are symmetrical pinacoles. So
Yeah.
first you will get any one side positive. Then phenyl is a better um, migrating aptitude, so that will move, and thus you will get this product. Okay. I have almost like 25 questions on this. I think some 30 odd questions on this. You have to go through all the questions, beta. Yeah,
Oh,
21. Got it?
oh, yeah.
This is only for advanced, but I would suggest better you go through all the questions. And lastly, check out glycerol. Or in this case, what we call it as glycerine, glycerol are one and the same. Okay,
Yeah.
right. See, how do we prepare it? It is formed by the side product of manufacturing of soap, which I told you already,
Yeah.
triglycerides giving sodium stearate, which is a soap, and
Hmm.
glycerol. Glycerol, when you react with red phosphorus iodine, notice that पहले सारे iodines आ जाएंगे, and you know that iodines are unstable. Remove this part, so you'll get this as the allyl iodide as the product. And if you react with 3 moles of HI, so you'll get iodine, iodine, iodine at all 3 locations. Remove one iodine, double bond will come. Again add HI, you'll get one more time iodine coming. Remove
Hmm.
iodine again, you'll get a double bond. Again add HI. So how many moles? 3 moles. Glycol में कितने आते? 3 moles.
3,
Glycerol 5 moles.
5.
Yeah, remember. Next. Ester formation, oxalic acid. Oxalic acid will make an ester. Then on heating, here heat I forgot. Heat is there. 110 degrees or 260 degrees. If it is 110 degrees, you will get directly acids here. Glycerol will be separated out, and this part will only get oxidized as acid and carbon dioxide. If it is at 2 degrees, then this entire part will get dehydrated. You'll get allyl alcohol, 2 moles of carbon dioxide. Okay.
Okay.
With concentrated HNO3, H2SO4, basically all of this OH and this H, just like esterification, better. Just like
Hmm.
esterification, you remove out this H2O, you will get this O nitro group here. This is called trinitroglycerine. And trinitroglycerine, TNG liquid. TNG liquid is nothing but a dynamite, explosive. Got it? Clear?
Hmm.
Just like RDX. This is also used as an alternative, TNG. Okay? Okay, next. This is used to be asked in polymers in mains, but now polymers is not there in the syllabus. But it can be
Yeah.
asked as a reaction of the alcohols. Glycerol, when you dehydrate in the presence of KHSO4, which is a dehydrating agent, you'll get allyl alcohol, sorry, vinyl alcohol, which is a enol form. This enol will convert into ketone, but you know that on further dehydration, you can always think this way, that this OH and this H can be gone and again a double bond can be formed. So you'll get
Yeah.
actually enol at this position, which on tautomerism will give you keto form, which is acrolein. So from here, you can get directly acrolein on using KHSO4. Okay. This
Okay.
was once asked, what is the structure of TNT? TNT is trinitrotoluene.
The explosive.
Yes, that is also explosive. Hmm?
Yeah.
Correct? Do you play Minecraft? No.
No, but I used to play Angry Birds.
Ah, okay. They also use TNT. Okay. Right. Clear? Hmm.
Yeah.
Okay. Last reaction is about oxidative cleavage. This is the last reaction of alcohols. Okay. Right. So if you take glycol, you react with HiO4 or Pb lead salt with a +4 oxidation state. In both case, you will form something like an ester form here. So this oxygen will connect with Pb, this oxygen will connect with Pb. Remove OAC two times. You will get a cyclic ester. Because it is connected with lead, we call it as lead ester. And lead esters are unstable form. The carbon-carbon bond will break. Here the bond will go. Here the bond will break. So what do we get here is aldehyde. The same logic applies to HiO4 also. This oxygen will attack from here. This oxygen will attack from here. It will become an iodate ester. And again the bond breaking is been done. And you'll get HiO3 and HCHO. But sir, mechanism is confusing. It's difficult to remember. Yes. So what you do, learn the shortcut. Shortcut is very simple here. Wherever you come across HiO4, if you find vicinal diols, that means adjacent OH groups, just simply break this, give one OH to the upper carbon, one OH to the lower carbon. Now notice the bond is broken. The upper carbon has two OH groups, the lower carbon has two OH groups. Two OH groups are unstable, that will convert into aldehyde. Here also it will convert into aldehyde. So what is the product? 2 moles of aldehyde. Done. Now compounds which are C double bond O, here adjacent to that we have C double bond O, acid, amine, any kind of alkyl amide. Even if these are present, the bond cleavage has to be done. Okay, check out. If you understand this example, means you are clear with it. Check. You have an acid, amine, so you can break it here. I give
Right.
one OH above, one OH below.
Hmm.
Again, between these two, one OH above, one OH below. So again, I'll give one OH and one OH.
Ah.
Again, here you can see OH double bond O above, so one OH and one OH. Again, I'll see OH above, so one OH, one OH. Again, I'll see C double bond O above, so one OH and one OH. Correct? So all of these OH groups have been there. Correct?
Yeah.
So after breaking, what do we get? The upper one has already one double bond O. Now get one OH. So what is that? Acid. Hmm?
Yeah.
The second carbon has one, one, one. Total three OH groups. Three OH will groups convert into acid.
Yeah.
Already C double bond O, and now you have two OH groups that will
That's
convert
right.
into carbon dioxide. Hmm?
Okay.
Because OH will remove as water. C
Right.
double bond O will be left.
Plus water.
Yes, this will convert into acid. This will, if you have NH2, this is amide, and amide on hydrolysis will again convert into acids. Okay.
Hmm.
And last one also converts into carbon dioxide. Clear, beta?
Yeah.
Right. So now you check out the last glucose structure once. This is the most important part of it. How does the glucose structure breakages and what is the product you will get? Check if you understand the breakages of breakage of glucose.
All of them are getting the same product.
See, this one, this
Yeah.
one, this one, this one, these four, and the fifth one. All of these are getting same products. They're all
Yeah.
becoming acid, and only the last one is becoming aldehyde. Okay,
Hmm. What?
yeah, right.
Yeah.
See the fructose case now.
Water.
Yeah, right.
Yeah.
Okay, rest of the cases you can go through it once. Okay,
Yes,
one
sir.
thing I just try to help you out here is this one. See, if because in the mechanism you notice that we have to get a cyclic ester. Cyclic ester is not possible if one OH is above and one OH is below, correct? Hmm.
Hmm.
So even though they are vicinal diols, if they are anti to each other, then there is no reaction. Okay.
Okay. Okay.
So in this case, there is no reaction. In this case, also there is no reaction. Done.
Yes, sir.
But even if there is slight angle between them, like both of them are equatorial here, so then the reaction can take place.
Okay. Got it.
Clear, beta? Right.
Yes, sir.
So this is all. This is the biggest topic of organic. Okay.
Yeah.
Maximum reactions are there here. Clear. So I think if you understand or if you practice this topic more often, you'll have a lot more similarities and you'll get almost a complete picture of organic. Okay.